So what we're going to do now is to look at the piles in laterally spreading soil. So this morning we looked at the lateral spreading soils, why that happens, and came up with a way of estimating how big these can be. So now what we want to do is to look at uh, what happens when piles are in place. So I think this kind of was prepared on the assumption that you know already PY curves, but let me explain a little bit what PY curves are, and then I'll explain this slide. Okay, suppose I have a pile in ground. Let's, for simplicity, assume it's rock socketed at the base, and it's subjected to lateral load. So what we know, if it was just a cantilever, it's going to bend outwards, and we can even calculate how much the deflection is. If I know the load H and L is the length, then you would say the delta is going to be HL cube by 3EI, right? So that is easy. Now, obviously, piles are not sitting in air, they are sitting in soil. So as the pile wants to deflect like this, it will be opposed by the soil. So one way you can see how much resistance I get is by imagining my pile is made out of lots of elements, and each of them has a horizontal spring. Okay, so when I am pushing like this, depending on how much deflection I get, I'll apply a spring force to oppose it. So if I know the force, I can divide that on the area of the element or projected area of the element, and that will be some form of pressure, right? So that will be the soil pressure generated to oppose the movement of my element. So far good. So each element will have some amount of pressure P, and that depends on the deflection, or if it is in air, we can work out how much the deflection is. If it is in the soil, we expect the deflection to be smaller. So what matters is the relative displacement between the pile and the soil. Okay, so that is called Y. So because we are using symbols P and Y, this is what the so-called PY analysis is. And people like Meyerhofen have done this for ages, for any laterally loaded piles in clays, sands, recent Matlock, and the rest of it. Now, it's also very straightforward to imagine that, so that is, say, element 1, and this is element 2. So I can imagine that my element 2 is here. I got some more pressure distribution there. Yeah. And there is a torsional spring between the two. So this is what you would call the structural spring, which mimics the bending stiffness of the pile. So this K rotational spring is there because we took our pile and cut them into little elements, right? Obviously, the real pile is all one unit, so it'll have bending stiffness. So we can say, oh, okay, I'll take each of these as rigid, and my bending stiffness is giving me the, I'm mimicking that as the rotational stiffness of the spring. Now, as I go deeper and deeper, my pressure goes up, but my deflection, the y, which is the relative displacement, I'll write it down clearly. Y is the u pile minus u soil. So, we should really call that a relative displacement. Yeah. So, what will happen as I go down towards the base? My relative deflection will get smaller and smaller, clearly, because it's trying to bend like a cantilever, right? But my pressure I get will be getting bigger and bigger. Understood? And the overall bending moment in the pile depends on the action between these two. Which is big, which is small, and therefore we get different bending distributions. So this is the famous PY analysis, nothing more than that. Only thing here is we may get this deflection of the pile and deflection of the soil. If my soil is going for walking down the slope, then that's going to be a lot bigger than what the pile can do. So if my soil is coming and attacking the pile this way, it's not the fact that I'm applying a horizontal load, but I'm applying a big soil pressure that's causing my thing to bend. But it's exactly the same concept as this. This is originally developed for lateral load on piles, but what we are now saying is our load or force action or load action is not coming because of some external load, but it's coming because of the soil trying to move downslope. Okay, in the context of lateral spreading. So all we learned so far, we can put them all together, and you can say, if I plot the relative displacement on the x-axis and the reaction force or P or pressure on the y-axis, you can come up with some very simple relationships like, okay, at some point the amount of pressure I can apply on the pile will be capped. Why is that? Why do you think that there should be a limit? So we have a PU ultimate, P ultimate. Why is there such a nice cutoff there? Can you think? Perfect. Yeah. So once you reach the passive capacity of the soil, it can't do any more. So there will always be some ultimate pressure. Perfect answer. So until that is reached, what we are saying here is, let's just say it's some linear increase, 0 till that point, and the slope of that is kh. Okay? So because that is force versus displacement, this is some kind of stiffness. Yeah? Okay. So this will be our relationship. Now what you can do is to say, okay, for the element number 1, I have that. Element 2, slightly bigger. So nth element here will have quite big force like that. So the PY curves we can change depending on depth, and then it gets quite realistic. So we are not saying one PY curve for all the elements. The PY curves themselves are scaled up depending on how deep you are. Okay? We're still not changing the stiffness. There are lots of things that are not quite right with it, but it is at least in UK we call it starter for 10. So for 10 points you can have a starter question. It's a game show thing, university challenge. Anyhow, so that is the basic idea of PY curves. Anybody not sure of what I said? Or is it clear? Okay, now we can put this in the context of we looked at different failure mechanisms, right? I've been showing for the last 2 days, and I'll show some more again, of how pile foundations can fail. I'm plotting axial load on this axis, yeah, and on the x-axis, I have increasing soil stiffness, and in the other direction, I got increasing pile stiffness. So as I go from left to right, imagine soil stiffness is increasing, and if I go right to left, pile stiffness is increasing. For example, the piles are thicker and bigger diameter. Then I'll increase pile stiffness. Going right, I may be having stronger and stronger clay, for example, right? And in this direction, we are having axial load. So what we first did, and you worked out yesterday for coursework as well, is if my axial load is quite big, yeah, piles will buckle, right? Whether soil stiffness, pile stiffness, you will always find in this space, piles will buckle, right? And how big this is depends on, of course, the pile stiffness, but also the end conditions. Is it free-headed pile or fixed-headed, pinned, whatever the structural joint is, that will determine the magnitude, but certainly it will be in this space. And the most important thing is these are all unstable states. Buckling is, as I said, keep banging on, is the instability that is the killer. That means you can't predict when it will fail. It will fail suddenly on you. So it is an unstable state. When the axial load is relatively small, if my soil stiffness is big and pile stiffness is small, what will happen? The soil is stiffer, pile is like thin guy, he'll get bent. So here I will encounter bending failure. Yeah. On the other hand, if my pile is very stiff and the soil is relatively weak, then I'll get more and more soil flow past the pile. So this is a neat framework to show. So all I really need to know is what is my axial load, what is my soil stiffness and pile stiffness, and I can then predict how my pile is actually going to behave, or how is it going to, how is it likely to fail. You like this? So everything we learned, we kind of are putting together into one unified state. Sorry. Yeah, please. No. Yeah, we will. This is the framework we are creating. Where exactly this falls, you need to populate that with data. Yeah, but this is. What I was trying to do is to say, okay, we saw all these individual cases, but there should be one overarching thing that holds it all together. In the end, I'll come and do this to say, especially for, we have done buckling bit, but for bending failures and soil flow, we will come and do this for single piles and pile groups, okay? Which is what he has been waiting for last 2 days. He keeps telling me. Right, so this is about the easiest PY curve people can imagine. However, there are slightly better ones. This is Tom O'Rourke and Go. Go is a professor, I believe, in NUS now. And back in 99, they came up with this shape. There are some good things and bad things about it. Let me explain. So here what you are doing is you are plotting the P on this axis and displacement on this axis, which is what our PY curve should be, right? Instead of plotting absolute values, what they have done is to normalize them. which is a good way of going about things. So the normalized force acting on the pile P divided by the undrained shear strength SU times the diameter. You should always make sure these are dimensionless, right? Let's just check that. P is kilonewtons over SUD. SU should be kilonewtons per meter squared, kPa, right? And D is the diameter. Also, I'll have, this is all done per meter depth of soil, right? Therefore, so this cancels, this is in meters, so that cancels, and therefore I'll end up with a non-dimensional group when I'm looking at force per meter depth. And similarly, this is also not, the displacement divided by the diameter of the pile will give me non-dimensional displacement. By doing this, what they could define the PY curve as, I mean, they have two, rough pile surface being rough or pile surface being smooth. So they proposed two curves, but you can define these with only 4 parameters. Slope of this line, KL, location of the peak, slope of that, and residual value here. So only 4 parameters are needed to define this. And this is kind of quite highly quoted paper, and it so happens that they basically over-constrained this problem. You actually should not apply 4 restrictions where there are only 3 variables. So that is called over-constraining the problem. If you do that, you can almost fit anything, any data to this, and it will work. This was pointed out to Tom when he was on sabbatical to us, and ever since then he respects us a lot more because we pointed out what is obviously a flaw in the model. Anyhow, but that is the, again, a framework for this. One of the, this is kind of better than this because this is assuming that I'll reach some PU and stay constant, right? What this is telling us is, yes, I'll reach some peak value at fairly small displacements, right? Then it will soften. So this is a negative slope, right? And you will reach some residual value. And this is quite good observation that when the slopes start to move for the PY curves, initial stiffness can be big. But as they continue to move, it will reduce the force because of lateral spreading, liquefaction, and the rest of it. And then you reach some residual value at the end. This, they have this parameter SU, P, and residual value, right? SU minimum. They proposed this for the, to work out how much they are. So the upper limit of SU, they say simply take that as 0.17 of the mean confining stress. The lower limit of that is 3.4% of the initial stress, initial effective stress, mean confining stress. Okay? So they also say it only takes 0.02% strain to drop from this peak value to residual value. Okay? So this is all like a nice recipe to work out the how the pressure on the pile can be calculated, or how the lateral pressure can be calculated. There is another issue which comes from a different source. The undrained shear strength of clays, we are mostly worried about clay because what I said in the morning, because of the clay crust on the top. That's where we will come back to. This, so clay will have undrained shear strength, which we all know or can work out. Simple UCS test should tell us that. But what happens when you subject the clay to cycles? It will soften. Okay, if you apply an earthquake loading to a nice clay bed, it will soften with cycles. And we have now got experimental evidence. Tejesh and other people have done this with clays, and there is enough data on that. Back in 95, this is a very popular paper where Liu and Dobry came up with this degradation of the strength. Suppose I have a multiplier coefficient for my strength of Cu. Okay, so when no cyclic loading is applied, it will be say 1. Yeah, if I cycle and mobilize a lot of pore pressure, then it will drop from all the way from 1 to almost 0.1, a factor of 10 drop. Typically, clays don't produce that kind of pore pressure. You'll get something like maybe 20, 30, 40 kPa, right? So it will be maybe 80% drop or 70% drop. Whereas sands obviously will liquefy, therefore they'll go all the way to 0. But this observation, this data from Liu and Dobry is very widely used and quoted, and it's considered to be pretty good. Okay? Okay. So far, these are all the things we need to know about piles and laterally spreading soils, and how we can adapt the traditional PY analysis to get the to fit into those models, right? Go and Rourke or somebody like that, that kind of model. What obviously I felt when we started this journey was that, yeah, but this is all based on cyclic triaxial tests and everything else other than actually doing proper physical modeling. So the first thing we did was to take a single pile and look at it using laterally spreading soils. So this work was done by my second PhD student and now my colleague, Professor Stuart Haig, and it was a real excellent piece of research. So what we wanted to do was obviously do the centrifuge test, but really we wanted to get the next to the pile, what are the stress paths the soil is going to follow. So near pile stress paths, we tried to do this using miniature pressure cells. Nobody believes earth pressure cells, or you should not put all your money onto earth pressure cells. Earth pressure measurement is one of the hardest things to do in soil mechanics. So we also had bending moment strain gauges on the piles to measure bending moment and the pile loads. Then what the prize at that point was that we can compare all this with design code. And the design code was being proposed by Japanese railway authority, I think JR8 it's called, and they came up with a design code, and we wanted to show that was rubbish. as you'd expect. And then I'll provide some conclusions on the single pile. So the experiment was dead simple. Just a single pile, no vertical load. The pile went all the way through the slope into dense sand. Yeah. But if I look at this on the plan view, we had actually two piles, one behind the other, because the width of the box is big enough. And this was another favorite of mine, where you can have in practice circular piles, but you can also have square piles. Some bridges and all will have square piles too. My idea was that if the soil is trying to flow down the slope, surely the shape of the pile should make a difference. Because if it is circular pile, I'll get nice continuous flow lines. If it is square pile, you get discontinuity of flow around it. It's same as any fluid mechanics problem. Okay? So this was the aim. So we had pore pressure transducers very close to the pile and also some earth pressure cells. So the input was sinusoidal. This is the old SAM actuator, and we applied something quite large number of cycles with about 1 meter per second squared will give you something like 0.1 G earthquake, right? Yeah, 9.8 meters is 1 G, so this is about 0.1 G shaking, and 1 hertz at prototype scale. So the genius of Stuart Haig was that I thought I had to spend a lot of money making square piles and circular piles and so on, and keep changing the stiffness, because one of the parameters is the stiffness. What he did was to say, no, we will use aluminum blades which are actually strain gauged to measure the bending. And then he made the rest of the pile with dense foam. So he could easily change the pile dimension, but the stiffness will be the same, because most of the stiffness is coming from the aluminum. The foam ain't going to do anything to this stiffness, but the foam will dictate how much load the pile will attract, because if I have a big diameter foam, I'll get more load. If I have small diameter, I'll get less load. So this is a very flexible pile design he came up with. Okay, so let's first look at the pore pressures on either side of the pile. So we got upslope at one depth and this 40 millimeter depth and 70 millimeter depth, and also at the same location on the downslope as well of the pile. So you can see that if these two are at the same depth, upslope and downslope, and these two are the same 3.5 meter depth, prototype scale, upslope and downslope. Firstly, although they're next to each other on either side of the pile, the response is very different, right? That much there should not be any controversy, because you can see that's gone up and doing that, this has gone up and these producing really big suctions here. Now, if I have an object like this and I'm measuring pressure here and on the other side, I can now take the difference between the two, yeah, and multiply with the area to get the force, right? So we could work out what is the these pore pressures, because they are different, how much force they are applying on the pile. This is getting less of an issue as you go deeper into the slope. These two look a lot more similar than these two, right? So the pile is trying to bend, and here at this shallow depth, they're very different, whereas at a deeper level, they're similar. And the deeper we go, the more similar they will get. Agreed? That's what the data is showing us. So we also did tests with flexible piles because we can change the blades, uh, and also relatively rigid piles. Again, comparing upslope and downslope. So these are the upslope ones and these are the downslope ones, flexible and rigid. So when my pile is rigid, I'm not getting upslope as much oscillations in my pour water pressure. When it's flexible, I'm getting a lot bigger cycles. And that makes sense. If the pile is flexible, it can do that a lot, and upslope, I will pick that up. If my pile is rigid, then it won't let the soil oscillate so easily, so I'm not getting those oscillations. So immediately you can see what the effect of rigid pile versus flexible pile is. Downslope, whether the pile is flexible or rigid, it's not making that much of a difference, right? So I'm getting big suctions here and also big suctions here. Does that make sense? Why do you think that is? You're not going to sit in my lecture and just drift off. I will keep coming back and asking questions. There, the pile is so small, the overburden stress on both sides is very similar. Big point is maybe that's what you're trying to say. Probably yes, probably not. I'm not sure. Basically, say the pile is here and the soil is flowing this way. When the soil is upslope, it's moving towards the pile. So if the pile is rigid, it is constrained, right? The soil on the other side, even if the pile is rigid, it's not being constrained going down slope. So this bit is always free to go where he wants to go, right? So this is why even for rigid pile, down slope, I'm getting all the oscillations. Okay? Upslope obviously will be similar, but downslope also, even if the pile is rigid, it will go. Yeah? So that is the reason why these are measured like that. Now, I can now even work out how much the hydrodynamic force I'm going to get, which will be the difference between the pore pressures at different elevations. And you can see how big these are. Again, these are calculations. Do you know why that is called? Yeah, okay. So flexible pile and different depths. These are basically plotted as the difference between the two pore pressures on either side. This is the direct force the pile will feel. So these are shown as pressures, but you need to convert that into, using the area, you need to convert that into forces if you want. So that is for flexible pile and this is for rigid pile. Okay, so far so good. But now we have the earth pressures. We can also look at these contact stresses, and you can see upslope and downslope, one depth and deeper levels. So again, you can see how big these earth pressures are or contact stresses are coming. This is going from naught to about 40 kilopascals. This one downslope, obviously, the soil is going away from the pile. So these are a lot smaller, right? And again, at deeper depth, this is even bigger than, this is almost 50 kilopascals of pressure. Here, almost just about 20. So Upslope, I'll get big earth pressure coming onto my pile. Downslope, it is disappearing. Although the contact pressure cells are not the best, at least they are doing the right kind of thing. Actually, they work better in this kind of earthquake problems because all the arching effects and all get destroyed when you start shaking the soil. So it's not as bad as in some of the static earth pressures you would measure. And this is where we feel proud of ourselves. Now we have the vertical stress and the overburden stress and the horizontal stress. We can plot the stress paths, right? Because we know the pore water pressure, you can plot the active earth pressure line and passive earth pressure line and see where my stress path is falling, upslope and downslope. So at 2 meter depth, so upslope the soil is trying to do something, starts here and ends up there. So clearly it's very close to being fully mobilizing its passive earth pressure capacity, fully mobilizing the passive earth pressure. Downslope, no, it's kind of oscillating between active and passive because that bit of soil element downslope is free to go where he wants to go. So no point generating more earth pressure than it has to. That's why it can oscillate between Ka and Kp quite nicely, almost equally. Okay? The deeper I go, the more cycling I do and more towards Kp I am. Upslope. Downslope, more towards Ka I am. So once you have good experimental data, you can get quite a lot of information on the soil stress state as well. And now you do this, if you ask your Plaxis or Abacus or whatever, plot me the stress path, then you know whether your code is working or not. If you have laterally spreading soil in Plaxis and say, next to my pile, give me the stress path, now you know where they should be. Upslope, it should be close to Kp. Downslope, it should be almost equal between Ka and Kp. If that pattern is not there, then there's something funky going on in your code. Because that's what you need. With FE models, you'll always get some result, right? But whether the result is any good or not, you need to be able to judge. And these are ways in which we, because we have experimental data, we know this, we put in all the thinking already and it is there, so you can take advantage of that. Okay? So that was for rigid piles. And these are for more flexible piles. The more flexible I am, these are all for 3.5 meter depth flexible pile on the top and rigid piles at the bottom. And again you can see, so this we have already seen, this one goes even further up the Kp line. And downslope, you are always getting these loops. And I already explained that. Now, from a design point of view, like most structural engineers, they don't really care for pore pressures, earth pressures, all that is for geotech people to worry about. What they want is bending moment. Will my pile take this or will it fail? So we obviously want to measure the bending moment. I've shown you the gauges. And these are at different depths along the pile, 1.25 meters, 2.5, 3.75. And as I said before, we wanted to see whether it makes a difference to have circular and square pile. Because it's all made out of blue foam, he could cut it either as square or circular as he wanted. And turns out, my initial hunch was not as hot as I thought it would be. So at shallow, I mean, if I shown you this and said that is for circular pile and this is for square pile, you'd say, well, if I change the titles the other way, you probably can't tell the difference. So from a bending moment point of view, in other words, the load that the pile is attracting was pretty similar. Yeah. So you would say not much difference. So we can't really optimize on the shape. But where it was, oh, okay, this is a bit I need to explain here. What we observed, I don't think I made the slide for it. I'm going to draw these in plan view. Say that is the plan view, that is my circular pile. What we observed was, say the flow is of soil is like that. Yeah? And for square pile, what we saw was it was going a lot more like that. So although the bending moment is the same, the zone of influence of a square pile was much wider than the circular pile. At that point, my thought was, really this is going to make a big difference when you have multiple piles, right? If I have a lot of piles, then each will say, depending on pile spacing, this zone will overlap with the pile in the next direction, and therefore the soil will have to make even more deviation and it can't flow in between the piles. This was back in 2001 when the student did his PhD. So I said, maybe we should put multiple piles. And he kind of threw his arms up and said, no, I've done enough work. I can't keep doing more tests with more piles. Maybe we'll do that later. Now it's 2025, right? This almost 25 years later. Now this thing has come up again, and he has a PhD student himself who's looking at many piles. This is a big problem in China. What they are trying to do is to create diaphragm walls by having contiguous piles. So if you have contiguous piles, it costs you a lot of money because every pile is next to another pile, next to another pile like that. That's how you create these walls. So they had the brilliant idea that maybe we can avoid some of the in-between piles and the clay can't squeeze past, which is exactly the same problem as this. So we are, after all this time, we are now looking at the same problem again for diaphragm walls. So anyhow, so the bending moment is the same, but the flow pattern is different. What that means is, although I attract the same load per pile, the where the load is coming from, the soil is different. So this depends on a lot more volume of soil applying smaller pressure, whereas this one is very focused but with higher pressure. So the sum is the same, but the volume is different. Okay, that's the extra bit I wanted to say there. Now, as I said, these people, Japanese rail authority, came up with this code, and they made a blanket statement. This is always bad in any code, particularly to do with earthquakes. They said, for any non-liquefied crust on the surface, where we started this morning, you can take 30% of total vertical stress and apply that as the lateral load onto the pile. Sorry, no, my fault. They're not that stupid. Sorry, the lateral pile loading. So I'll draw the picture from the morning. My apologies. So this is the sand, liquefied, and this is the clay. So what they're saying is, if I go to pile, going like that, here apply Kp. Use Kp to work out the horizontal pressure. Fair enough, because that is clay. For all this, typically this is 1 to 2 meters, and these are 10 to 15 meters, especially in Japan, right? So they're saying take 30% of the overburden stress of sigma V, not dashed, and apply that as the lateral pressure. Where they got this 30%, nobody knows. It's just a number they picked. So we thought, hang on, we've done all these tests. Surely we have the data to see whether this is conservative or unconservative. And here you go. These are the bending moment with the depth. Yeah? So the JRA production, we basically use this rule to calculate our the bending moment in the pile, and that is what JRA gives you. From our own experimental observations, this is the bending moment variation with depth. Yes, the square and circular piles are pretty similar. As I said before, they're not that different. But if I compare this to this, I'm underestimating my bending moment by a factor of, say, at a depth of 4 meters, this is maybe 70, and that is more like 160. So a factor of 2, right? What is the normal factor of safety people use on pile design? About 2. So this is why a lot of these piles are failing. Okay? So when you do tests like this, you can then go and challenge any existing wisdom. I'm not blaming JRA fully, because they are the ones with the problem. Earthquakes are happening every time. They have to have some rule which engineers can use to design. But in their haste, they didn't consider a lot of these very carefully. Although they say use Kp, because the thickness of the non-liquefied layer on the top is quite small, even if you add that, it comes to be a fairly small value. Yes, the pressure is more, but it's only on thin layer, whereas most of your pile is in the liquefied soil layer, right? So this is bending moment. This is the net horizontal stress. Again, that is quite small compared to where we were making our own measurements from the unreliable contact earth pressure cells. But at least you can get a similar order of difference in magnitude between what they are saying you should use for design and what we were measuring. So we wrote back to JRA saying this is our observation, and they never came back. When it is convenient, they don't understand English. Anyhow. So, in summary of single pile, what have we learned? We are very sure that soil dilation close to the pile causes this transient loading. That's why you're getting those suctions and differential earth pressure, pore pressures. And as liquefied soil wants to go past the pile, it gets sheared. And if it gets sheared, it goes it tries to create suction, and that means it gets stronger, therefore it can apply bigger load. This is the underlying mechanism that is causing us all the trouble with this problem. Okay? So, more flexible the pile is, less load it attracts. That's fairly obvious to say. You know, in engineering, the basic principle is that of unstoppable force and immovable object. Have you heard of that? No. Okay, this is like a common thing in physics. If I have an object, yeah, on which I can apply infinite force, right? Normally, if I increase the force, the object will move, right? But if the object is immovable and I can apply infinite force, then I can keep applying bigger and bigger force, and because it can't move. So that is not possible in physics. At some point, the body will move, right? So if the body is able to move, it will attract lesser force. And the same thing applies here. This is the pile flexibility reduces the load it attracts. Square and circular piles, to my great disappointment, attracted the same loading and created the same bending moment. However, what we observed was the zone over which it mobilizes is different, especially at the peak load. And the JRA code underpredicts both the peak bending moment and peak horizontal earth pressures by quite a lot. Okay? Residual values are comparable. Once the earthquake finishes, what they get is pretty similar to what we got was similar to JRA's predictions. But the whole point is your pile has already failed during the earthquake. So whether you got the residual value or not doesn't really matter. This is just to save. You must always give some room to save their faces, otherwise they feel bad. So oh, you got residual values, okay. Your peak values are a factor of 2 off, so your pile has died during the earthquake, by the way. Okay, now I need to go into pile groups in laterally spreading soil. Do you want me to start this now, or do you want to go for lunch and come back? It's up to you.